Hello and welcome to this video on Grand Challenge 1.3 of the FEMM Hub. I'm Dr. Jill Miscandlon from the Advanced Form and Research Centre in Glasgow, and I'm going to take you through a very brief overview of the work that we've been doing as part of this Grand Challenge. So Grand Challenge 1.3 is looking at the manufacture of lightweight and multifunctional components. We've got a whole host of researchers and academic staff working on this Grand Challenge, mainly from Sheffield and Strathclyde. And we've also got a PhD student who's associated with the Grand Challenge, Charlie Scott, who's looking at lightweighting of non-active components. So Charlie's got a video which is going to be on the website too, so I would highly recommend going to listen to him talk. The aims of the Grand Challenge, they're summed up quite nicely in the title, but they are basically looking at lightweighting the non-electromagnetically active components of an electrical machine, and enabling these components to improve the overall efficiency and performance of the machine through intelligent design of the components and making use of some advanced manufacturing techniques that weren't available 10, 15, 20 years ago that can get us a lot more detail and advancement with the actual geometries that we can manufacture. While striving for these two key points, we're also aiming to achieve them while optimizing the method of manufacture. So potentially reducing the part count to aid with the assembly of machines, or reducing manufacturing steps to help with the overall costs and the lead time for components. So in order to do this, we've got four main research objectives that we're focusing on. The first one is looking at a systematic review of current practices of machines, current requirements for different sectors, different applications, different types of machines. The first few months of this work package were really a chance for everyone to get up to speed, because a lot of people working on it that had a manufacturing background had never worked in electrical machines before, and a lot of the people that were working in the electrical machines side of things didn't have a huge manufacturing background. So a lot of what that systematic review in the first instance was trying to get us on a level playing field where we could bring the requirements capture from the design and the manufacturing side into a single piece of work. The main thing that I'm going to be talking about in today's video is the advanced forming case studies. So really taking specific types of machines or specific geometries of machines and get into it in a lot more detail to be able to look at process developments, integrating features in there, and actually doing some of the more technical side of the work. I should say the slides that I've got today aren't overly technical, just because I've got quite a short time to talk about a lot of things. So if there is anything that comes up in the slide pack today that you're interested in, that you would want to get more information on, please feel free to get in touch and I'll put all the contact details at the end of the video. The final two research objectives are around alternative materials, so emerging materials for lightweighting and polymer composites, and the use of metal composite hybrids, sorry. It's not something that I'm really going to go into today, as I mentioned, with the time constraints, but it is something that is ongoing within the Grand Challenge. So like I said at the start, we had a group of researchers where they either had an electrical machines background or they had a manufacturing background. So a lot of the earlier work that we did as a group was really to understand the requirements of the other side, to see how we could make a huge impact on the design and manufacture of these machines. So one of the first things that we did was we conducted a value analysis session, and we used an aero engine starter generator as a test case. You can see the link for the paper there. The interesting thing about this, not only did it have an aerospace application, but almost half the weight was from the non-active components. So when I'm talking about non-active components, we're focusing on the rotor shaft, the rotor hub, the end casing, tubular casing, and the containment sleeve. So this, the machine in this paper had been optimized from an electromagnetic point of view, but not so much from the non-active components side of things. So what we did for the workshop was we listed all the electrical machine requirements, scoped them out in terms of functional, mechanical, and thermal fluid, We also looked at the material selection for all the individual components and what the current method of manufacture would be. Again, bearing in mind that the machine in this paper was a prototype and isn't something that's in full production. We then went through the value analysis session, and we came up with 19 new ideas on how we could potentially manufacture these components. The ideas were then scored against drivers which we'd selected, which included efficiency improvement, weight reduction, and various others. So the two tables that you can see at the top there are just a sort of summary of some of the ideas that came out of this session. So on the left-hand side, we've got them ranked where we've got the highest score for each of the individual components. And then on the right-hand side, we've got the 5 overall top scores. So you can see there's a whole range of things in there, from radial forging of shafts to wrapping of composites and additive manufacturing of the end cases. And again, a lot of those would come out of looking at reducing weight and taking material out of the components. So the main outcomes from this initial session was that alternative methods of manufacture could be found, multiple methods in some instances, for all the non-active components. And we felt that implementation of those methods of manufacture could provide improvements in the weight reduction and the efficiency of the machine. However, the scale of the improvements were not likely to reach the very adventurous performance requirements that are out there at the moment. So for example, the power density of 9 kilowatt per kilogram, which is in the APC roadmap for electrical machines. So we came to the conclusion that changing the manufacturing method for each individual component simply to remove weight from it wouldn't be enough for our machine to be able to reach its power density requirements. So this then led on to a manufacturing workshop, which I'm going to go through now. So this workshop was held with all the members of the FEMM Hub, all the active academics, and basically we were looking at creating a baseline status. So what are the current supply chain capabilities? So we set out active and non-active components and listed all the individual components, so you can see an image there for the non-active ones. Went through for each of the components the current supply chain, what previous research experience the FEMM Hub partners had, and where these components are sort of fitted into the future research direction of the FEMM Hub partners. We then collected information on the preferred method of manufacture for each individual component, the availability in the supply chain, so are these commodity items or are they limited availability, are they very bespoke? And then again, we linked it back to the individual grand challenges within the FEMM Hub. And for us, some observations came out from the baseline mapping exercise, one of which was the supply chain is not extensive for electrical machines in the UK. There is a supply chain there, but most items have limited availability, or they require you to go to a specialised supplier. And perhaps most importantly for Grand Challenge 1.3 is that there was really no research previously conducted within the FEMM Hub group on the optimization of the non-active components. So there was a lot of effort put into the optimization of the active components, but then the design of the active components then led to, we just need a rotor hub, or we just need a case to encase these things, and there was no development for them. So the next step was, we know the baseline status of all these individual components, but how can we make improvements for our electrical machine to really achieve the significant performance improvements that we need? And it was a case of anything's on the table. There was nothing prescribed. It was just a case of, if you had an optimized machine, what kind of things would you have in there that would actually help you achieve the power density requirements that you need? And when we did that mapping exercise, there were key themes that came out of it. And you can see the 3 high-level themes. We've got increased torque density, through-life maintenance, and repeatability and process control. And then within each of those, of course, there were sort of other lower-level themes where there were lots of ideas generated for what could help. For example, what could help the thermal management of a machine. So then what we did in the workshop was we grouped all these ideas into general topics. and assigned them to all the different grand challenges. So for Grand Challenge 1.3, this was the list of themes or topics that came out of that manufacturing workshop. So we've got a whole range of things, from cooling designs and additive manufacture to part count reduction to modular design of an electrical machine. There were most of the items that came out of the workshop really did focus and link quite well to grand challenges that were already in the FEMM, but there were what we called at the time alternative considerations, which really didn't fit within any particular grand challenge. So these are around recycling and sustainability and through life maintenance of the machine, so reuse of magnets, design for disassembly, and it was quite obvious that these were really key things, and at the time we didn't have anywhere where they sat quite nicely. So now we have a new Grand Challenge, Grand Challenge 2.5, which was launched last month, so October 2020. And there's a video on the website for that, for anybody that is interested in sustainability and circular economy for electrical machines. So moving back to Grand Challenge 1.3 now, you can see that we've got a list of topics there. Our next stage was to take those topics as a guideline for the sort of type of work that we wanted to move on to do, the type of research that we were looking at. So the one that I'm going to talk about now is the rotor hub and shaft design and manufacture, and it really came out of sort of advanced forming uses for lightweighting and a little bit of part count reduction, and I'm going to go through some of the work that we've done on this rotor hub and shaft. So the aim of this stream of work is to lightweight and cost effectively manufacture a rotor structure of an electrical machine for an aerospace application. And you can see there on the right hand side that we've got a flowchart. And basically what we're trying to do is we're trying to develop a methodology where if we have an application in mind and we have certain requirements, how do we go through a logical process that takes into account the design requirements, but also the manufacturing considerations, so that we get an optimized solution, an optimized design of that rotor at the end of the day. And we're looking at modelling objectives, which is to identify alternative rotor structure designs, analyse the deformation and mechanical stresses, study the dynamics of the rotor shaft bearing assembly, and seek potential for lightweighting. And all of this while considering the manufacturing process. And that's probably one of the things that's novel about this piece of work. You know, a lot of people have looked at how to lightweight a rotor, or using modelling to justify design choices. But what we're trying to do is bring the manufacturing into it at the same time. So we have a hollow coil demonstrator machine, which is getting used as a baseline for the study. It's a surface mounted permanent magnet electrical machine with a base speed of 10,000 RPM. The original rotor hub shaft design, which you can see in the image on the bottom left there, has got a central hub, a hollowed out hub with end shafts, which have conical sections on them. And this was the first design option. From a manufacturing point of view, that's quite difficult to manufacture the individual components, but then also to assemble with a shaft that has got good run-out properties. It's quite tricky. So then the second iteration, the below right, we took a step back to a more traditional design where you've got a hollow through shaft, you then get a spoke hub on the outside and your other components on that. That spoked hub is also manufacturable, but the fact that we were looking at a titanium alloy for that part, it severely reduces your potential methods of manufacture. So once we'd gone through the initial design considerations for these two parts, it then got us thinking, well, how do we develop a methodology that systematically considers the design and manufacturing in a single process? So this is where we're at just now. We've got a family tree of a rotor hub and shaft. So if you've got an internal rotor, you've got options where you can have a separate hub and shaft, or you can have a single piece hub and shaft, and then depending on your choices, you can flow down and you get multiple different options for your final hub and shaft assembly. And you can just see some of the ones on the right hand side here. We've got 4 different designs that are detailed there with the CAD and then the cross section, just to give you a feel for the variety of combinations that you can get with the hub and the shaft. So what we're doing is looking at the original family tree diagram, working down, picking 3 or 4 of the alternatives, and then actually looking at going into some detailed design. And as I mentioned right at the start of this video, there's not a huge amount of technical detail in here. This is probably the only slide that's got really technical information on it. But if there's anything that you're interested in, please do feel free to get in touch. This is just a summary of sort of one idea of the analysis that we're doing. So it's a 1D model focused on the low order critical speed prediction and looking at how the wall thickness changes and the bearings affect it. So as you can see here, if you've got a minimum, if you've got a wall thickness on your shaft of 7 mil, you've got a rotor mass of almost 7 kilograms. If you can reduce that to 2 mil, you lose 30% of the weight, and you also are able to shift your first order critical speed up by sort of almost 4,000 RPM. So that is some of the work that we're looking to do. Obviously, when we're talking about shafts, we're talking about multifunctional components. So can we manufacture maybe splines inside the shaft so that we can help with airflow, or can we just use a technique such as radial forging that will allow us simply to take weight out of this shaft by reducing our wall thickness from a sort of nominal 7 mil down to something or 2 mil. How far can we take that, and how much weight can we get out of the machine while either maintaining the properties of the machine or even improving them if possible. So the final thing that I just want to mention in this video is a little bit of work that has started recently on systems integration. So for the FEMM Hub, obviously we started initially looking just at the electrical machine, and that is still the main focus of the hub. However, recently, again from the manufacturing workshop, a lot of questions came out about if we do make these design changes and we implement them in an electrical machine, what then does it do to the wider system? What are the implications for the wider system? And what implications do we have to take responsibility for? So for example, in an application where you've got a premium on power density and efficiency of the electrical machine, those two things are often at odds with each other. Where do you put your priority, and how do you optimize those as a pair? And one of the things that we've been looking at recently is, for example, if we're improving the performance of the electrical machine through cooling techniques, how do we get an optimized cooling regime, not just for the electrical machine, but for the system that it's integrated in? And one of the questions we could ask is, at what point could an air-cooled machine perhaps become competitive with a liquid-cooled machine, but at a system level rather than at a machine level? So for example, if we had an air-cooled machine and we wanted it to work as efficiently as a liquid-cooled machine, it would need to achieve X, Y, and Z. For us, in order to achieve that, how do we make use of some of the novel manufacturing that we have at our disposal so that we can actually achieve this criteria? So one of the things that you always have to look at with systems integration is, originally, how do you define your boundary? What do you include? What do you exclude? And this is a bit of work that's still ongoing. We're looking to develop some methodology around this. So at the moment, we're looking at things like TRIZ, which is a high-level conceptual stage, sort of structured brainstorming, axiomatic design, which takes your concept stage to a detailed stage, and then something like multidisciplinary optimization, when you've got a baseline design stage, making changes and then tracking those changes to see how it affects your system. This is still quite early in its use. It's not a methodology that is up and running yet, but it's something that I think could be quite exciting, especially with the integration of the manufacturing issues in there as well. So I'm almost at my 20 minutes, so I'm going to stop talking. I hope that was informative. Like I said, not a huge amount of technical detail, but we have all the technical detail to back up everything in the slide pack. So please do feel free to get in touch if there's anything that interests you or anything that you feel you could contribute. And in a discussion about these types of research questions. So myself and Merad are the two main people to contact. We've also got LinkedIn, Facebook, and a mailing list for the hub. And I'll just leave the hub partners up there as my final slide. And thank you very much for listening.